back into the right mindset. We've got our soil, we've got a tree. It's my artistic rendition of a tree. And of course, that tree has some roots. And we've already learned that all of this is in one way or the other driven by our friend the sun. And we know what the little plant does in the whole system. The plant takes up carbon dioxide and releases O2, but the release of O2 is a side product. Really what it's doing is it's assimilating the carbon, creating an energy-rich structure, sugars of sorts, and using that sugar as energy to make lignins and starches and grow and become the primary producer for ecosystems. So in the process of that, the respiration then goes the other way around. So in the root zone, we are taking up oxygen to regain the energy, and we are releasing CO2. And in order to make the whole photosynthesis and respiration happening, we also need to have water. So H2O being taken up by the root system. Okay? So we've explored all this stuff in detail, and now we're going to look at the gas phases and see what the gas is doing here. So in the atmosphere, we would expect to have an oxygen concentration in the order of 20%, a CO2 concentration in the order of 0.04% or 4 parts per million, a nitrogen concentration in the order of almost 80%, 78%, and a relative humidity that's going to vary dramatically. So let's say from 1 to 100%. So in the soil, this is all a little bit different. So here we have an oxygen concentration that is going to be much less. So O2 soil is going to be much less than O2 in the atmosphere. And we already know why, because the oxygen is being taken up for respiration. And that's, of course, not just by the plants, but by every other life form in the soil as well. And because the oxygen concentration and the CO2 concentrations in the soil, they always go hand in hand. If one goes up, one goes down, and the other way around. So in proportion, then the CO2 concentration within the soils is much higher than the CO2 concentration in the atmosphere. So the nitrogen concentration, the N2, the dinitrogen, is no different, 78%. Why? We've already explored that. That form of nitrogen is not bioavailable. Plants can't do anything with it. Microbes can't do anything with it. So that just gets exchanged with the bulk air, and the concentration of it is indistinguishable from the concentration in the atmosphere. And the relative humidity, so how much water we have in the soil air, well, that's quite different, because in the soil, we are almost always pretty close to saturation. So 900 to 100% relative humidity. Right? So that's sort of a recap of what we hopefully already know. And now we want to explore why these differences come about and what happens if these differences are pronounced, and what if they are not as pronounced. Okay. So in this exchange, I'm going to just basically repeat the same thing, put a different plant here. We need to be moving primarily oxygen into the soil. So O2 in and CO2 and other byproducts out. But those are the two main ones that need to be exchanged. So in this gas exchange, if this is a really fast and rapid gas exchange, then we would call the soil aerobic. Okay. Versus if that the exchange were to be slow and oxygen was to be limiting, then we would call this anaerobic. And then there's another term that goes along with it. If there's lots of oxygen available under these aerobic conditions, we might also call this an oxidizing environment. Versus if it is slow gas exchange, we've gone anaerobic, then that might be a reduced environment. So some new terms to add to our repertoire of complicated terms. So it's basically, oops, a bit like this. Okay? So that's the big picture. Now let's look at this gas exchange a little more in detail on an example. And the example I have is to do sort of a back of the envelope. Oops, I just wanted a new slide. Oops. Let's just go to the beginning. Yeah. So back of the envelope kind of calculation. There you have it. Okay. So now let's say we have a root zone. Okay, there it is. And this root zone is 1 meter squared surface, and it's 0.6 meters tall. Okay? And in this root zone, we have an air-filled porosity, theta, oops, not Q, theta air, that is 15%. So this is the air-filled porosity. And what air-filled porosity is, theta air equals the volume of air divided by the volume total. So the definition is very similar to the volumetric water content, except we're looking at the air content. And let's say we have roots and microbes and everything else in there that gives us a respiration rate. And the respiration here is, what did I write down? Equals 0.01 kilograms of oxygen per meter squared of soil per day. And the question I have is, how long does it take to deplete that amount of oxygen if there's no gas exchange whatsoever? Okay. So the time to depletion without gas exchange. That's the question. Okay. And I know you all like calculations, and I read lots of comments that the calculations are frustrating for you and that they're hard to follow sometimes. So I'm going to try my best to narrate this a little better, but feel free to interrupt me whenever something doesn't seem clear, or where did this number come from? Why are we doing this now? So interrupt me. We can make these work for you. Right? And I know you don't like them, but it shouldn't mean that I should stop doing them. Maybe that should just mean that I should do them more so that they become more second nature to you. Right? So let's calculate this all out. So first step maybe to calculate this out is, well, let's figure out how much oxygen there is in this particular root zone. And since our respiration rate here is given in kilograms of oxygen, why don't we try to figure out how many kilograms of oxygen are in this air? So first we're going to figure out the volume of the soil. We're going to figure out the volume of oxygen within here, because we know it's 20%. And then we're going to convert it to kilograms of oxygen. Once we have that, it's pretty easy. We know how much there is, we know how much is being used, and then we can figure out how many days that oxygen might last. Right? So that's the game plan. So let's start out with the total volume of soil. That's easy. right? So the total volume of soil, VT, is simply the area times the depth, or 1 meter squared times the 0.6 meters of depth. So we have 0.6 meters cubed. Fine. Now the volume of soil air, well, that one is the total volume times the air-filled porosity that gives us the volume of air we have there. Right? So that's not too bad either. Volume air equals volume total times theta A, or 0.6 meters cubed times 0.15, and that gives us 0.09 meter cubed, which is also equal to 90 liters of air. So now we know that 90 liters of air, and we do know what the concentration of oxygen is. So now we can figure out what the volume of O2 is, right? So volume of oxygen, that is then simply, so the volume of O2 equals the volume of air times 20%, the concentration of oxygen in the atmosphere, assuming that we created atmospheric conditions and then we shut off gas exchange. So that then is simply 90 times 0.2, so that's 18 liters of oxygen. Okay? So now we want to take these this liter number and see if we can figure out how many kilograms or how many grams of oxygen that is. Okay? So in order to do that, let's remember back to some old stuff. And it says that an ideal gas occupies 22.4 moles per liter, and 1 mole, oops, what are we doing here? And 1 mole of O2 equals what? Okay, so for that, it works out that we're working in a chemistry building. So oxygen, 16 grams per mole. It's an O2, so 32 grams per mole. So 32 grams of O2 per mole. So with that, all we got to do now is to calculate this. So the mass of O2 in the soil air is now I'm going to convert the grams of O2 to kilograms, so that is 0.032 kilograms of O2 per mole of air times the 18 liters we had of O2 divided by the 22.4 moles per liter. So now mole and mole cancels out, liter and liter cancels out. So what we're left over with is an answer in units of kilograms of oxygen. And that is, if you type this all in, 0.026 kilograms of O2, not per anything, that's just it, kilograms of oxygen. Okay. So this is how much oxygen we have in the soil air. And our respiration rate is 0.01 kilograms of oxygen consumed per meter squared per day. So in other words, in 2.6 days, we would be out of oxygen if it's not being replenished. Right? So 2.6 days is what we have. So 2.6 days to 0 oxygen. That's the final answer. It's yellow. Nope, that's black. Yellow. Okay. So with that, we clearly need to have some kind of mechanism to replenish the oxygen in the air. And that's what I want to explore next. So there are a number of mechanisms that make this all happen. Okay? So as gas exchange goes, you already have this figure. You don't have to draw this down again. I just put it up here again because I don't have it again. There is my little plant. We need to get oxygen in, and we need to get everything else back out. So how does this happen is the question. So the first way that this may happen is, especially in terms of oxygen, to have the oxygen dissolved in water. And whatever water enters the soil has a little bit of dissolved oxygen in it. And that's one way to replenish the amount of oxygen there. So as dissolved O2 in water. So these are mechanisms for exchange. I should put this here. Okay. So the amount of oxygen you can dissolve in water in terms of replenishing oxygen in soils is probably fairly minor. Right? So it's a good mechanism, but let's say it's pretty minor. Not terribly important. Right? Number two is in terms of convection. Okay? Which, you know, convection would be, got this big door here, with lots of oxygen there, much less in here because we're all working hard with our brains. But there's enough of an air movement here, right? I mean, these guys here move air through it all the time. So the oxygen from the outside is being replenished in here as part of the bulk air movement. It's not just the oxygen itself that uses it, but it's everything, the nitrogen, the water vapor, everything, and the oxygen moves in its space. That's what convection is. Everything moves in bulk. It's a whole of air movement, including the oxygen in it. Okay? So what makes this all happen? Well, fans do, but there's not too many fans in soils. So it's temperature differences. Right? So if you think about soil, relatively constant temperature, but then when you get above the soil in the atmosphere, big swings of temperature, right? And these temperature differences, right? The cool air in the soil and the really hot air above, that's going to induce a movement of air between these two, okay? So temperature differences between soil and atmosphere. Or you just have an atmospheric event go through. Right? A big cold front, right? Brings a lot of rain with it. And this big cold front brings lower pressures, right? Low pressure system. And the air pressure within the soil may now be higher than the one in the atmosphere. Induces an air movement, right? Or the other way around. Right? Any of those will induce some convection. The other ways that happens is with the infiltration of water. Remember when we talked about infiltration? And we take a dry soil, we dump a bunch of water on top of it, and that water moves through the soil as the saturated region, kind of like a piston moves through the soil. Well, any air that's under it, right, it's going to get pushed through the air, right? So it's just going to move air through it as a convective movement. And then number 4 is water uptake by plants. Now it's kind of counterintuitive, but think about it this way. If a plant takes up water, that water occupied volume within that soil. Now, if that volume gets pulled out of the soil, that leaves a void, which means that air can rush in from above to replenish that. Okay? So it's all convective movement. And to stress this one more time, that convective movement is a bulk movement. Okay? So mathematically, we can express it as Q convection, okay, which is a volume of air per cross-sectional area per time. These kind of themes repeat a little bit, don't they? And oops, that's not an equal here. That should be a multiplier. That gets multiplied by, oh, actually it is an equal there, minus kappa, and then a nu, I should have left a little more room, times a pressure gradient. So delta P over some distance. All right, let me label all this. Okay. So the nu here, we already know that one. That's the viscosity. In this case, the viscosity, of course, of air. So the more viscous fluid, the easier the exchange. The little k here is the permeability, or the gas permeability. So that's going to be a function of the pore architecture, right? Does it have little pores, big pores? How well are they connected? What are the shape of these pores? So that will just say something about how easy is it to move a gas through that soil as a function of the pore structure of that soil. Okay, so this is going to be a function of pore architecture. So the gas permeability of a sand is going to be way higher than the gas permeability of the clay. Okay? And then the rest in here is this delta P, so it's a pressure difference or a pressure gradient. Right, so that's what makes it all work. And then the L is just a physical distance. Okay. So it looks just like the Darcy law in some ways, right? A flux, a flow of air per cross-section area per time is accomplished due to a driving gradient. So the thing that makes it all work is this. Now it's a pressure difference, just like it was before. But the thing to point out is the total pressure of the air, right? So it's not a partial pressure of oxygen. It's the total pressure of the air, right? So it's 101 hectopascals here, and it's 105 hectopascals out there, and that's what makes air move. And then this piece here is just, well, the pore architecture, how easy is it to get stuff through it, and then we've got the viscosity here, this property. So that's convection, which can sometimes be quite important in soils. Okay, so as an exchange mechanism, if you have really, active atmosphere, you've got water uptake, rain, infiltration, all these going on. This can contribute to a large amount of the gas exchange that's needed to get oxygen in and CO2 out. But there's a third mechanism by which this all works that oftentimes is the most important one. So number 3, oops, didn't mean to stay in red here. Let's go back to black. Number 3 is diffusion. Let's just say most important, most always. One can always find exceptions, okay? So with diffusion, the little flux equation I just wrote out changes just in a really small way. So now this is a Q diff, diffusion, which again is a volume, but now, might be a volume of O2 per cross-sectional area per time. And that's now a minus ds, or that's a diffusion coefficient times a concentration gradient over some distance. Okay, so let me label this business here again. So ds is a soil air diffusion coefficient. Okay. And the delta C here is a concentration gradient. So the big difference here is things aren't moving as a bulk air anymore. So now things are happening in accordance to concentration gradients in individual constituents. Okay? So there's no bulk, let's just say, you know, we shut the air system off, there's no bulk air movement between the hallway and this. But we are consuming oxygen in here, and out there they're producing the plants. Right? So we got less oxygen here, more oxygen here. Things are going to exchange to an equilibrium based on that concentration rate. At the same time, we are spewing out a whole bunch of carbon dioxide. There's less carbon dioxide out there. There's going to be a gas exchange of carbon dioxide in this direction because the concentration gradient is up. Okay? It does not need a bulk air movement. We're just exchanging individual elements within it. So this diffusion coefficient that describes how quickly that exchange happens. Well, in soil air, this one can be rewritten a little bit. So there's a ds here. You could look at this as related to what's called the d naught, or which is a free air diffusion coefficient. Okay. So we're just here, you know, we're surrounded by air, more CO2 out there, less in here. This exchange does not happen instantaneous, right? There's some kind of a conductance term in a lot of ways. So that's what that diffusivity is. So there's some resistance to that exchange, okay? And that's what's described by this free air diffusion coefficient. Within bulk air, CO2, in order to get from there to here, experiences some kind of resistance or conductance, and that's what's expressed with this free air diffusion coefficient. But in soils, well, we've got this stuff in the way, right? So the air is interrupted by the particles. So we're going to have to scale that all to say that, okay, so we're going to have a air-filled porosity, so a volumetric air content, which multiplies this number to get to a diffusion coefficient. So we just had an example, 15%, so 0.15, right? So in other words, the diffusivity in soil air for that example would be 15% of this number. Right? So it'd be, you know, a good bit slower than it would be if these soil particles weren't in the way. Okay? And then, of course, that's not all of it, but then the pathways here also get interrupted by water, right? And then whatever gas exchange there is has to travel through here in these tortuous ways. So once again, there is the tortuosity here. And we should probably put that tortuosity in here as another multiplier, as an inverse multiplier. Okay, so the diffusivity decreases by how little air we have available, and it also decreases by how much more that pathway has to be tortuous to connect from one side to the other. So overall, a pretty slow process, but the most important one in soils, which of course now also tells you that, right? So that gas exchange due to diffusion is going to be much more effective for short L's, so close to the surface, right? And as you get further down into the profile, well, that exchange mechanism becomes less and less effective. So yet another reason for why a lot of the roots are concentrated close to the surface, because that's where that gas exchange is going to be at its highest magnitude, and you get a lot of the turnover and activity there. Okay? All right, so that's that for this. And there's more to the story here, and that is the free air diffusion coefficient here. So if you compare the D naught gas with the D naught water, you would find that, surprise, surprise, the diffusion coefficient, doesn't matter whether you're looking at oxygen, CO2, or ethylene, or anything else, within the gas is way higher than within water phase. Okay? To the point where, so if you're looking at oxygen itself, it'd be a ratio of 10,000 to 1 for oxygen. And then you couple this with the whole thing being multiplied by how much air you have and the tortuosity there. And the end result being that a waterlogged pore, so any blockage within this little red pathway that I have here, any little blockage, so you put a blockage here and that would shut off the gas exchange altogether, right? So if you're, let me back up and say it's more than that. So the diffusion through gas is orders of magnitude faster than through the water phase. So if diffusion had to happen only through water-filled pores, it'd be almost nothing, right? Or it would be nothing. So with that, if we're now looking at oxygen exchange through soil or CO2 exchange through soils, we really rely on gas-filled pathways to make this all happen, right? If I have a discontinuity in here, I just have a water-filled pore here that blocks that diffusion pathway would shut down and we would have zero gas exchange with water blockage, okay? So that's why waterlogged soils are the ones that are depleted in oxygen, because gas exchange through water makes, okay? So waterlogged soils block gas exchange. Logged soils gas exchange. Highlighter, not eraser. Whew, that was close. Okay, so there's your bullet point right there. So with that, let's do some more complicated stuff. That's all fine and good. Now we know how gases are being exchanged, what kind of mechanisms are active there, which one is the most important one, and why water is such a big deal in gas exchange, because water means no gas exchange. Right? So, and now let's complicate the whole thing and start thinking about this oxidation, reduction, and oxygen availability in soils. And I'm going to do it in a really complicated way, which hopefully pays off at some point in time. Okay. So we have looked at the water molecule at some point in time. There's our little oxygen. And that little oxygen had these electron spheres around it, right? And there were 8 electrons. Let's make them red, okay? So 2 in the inner shell. And then we had 1, 2, 3, 4, 5, 6, 7, 8 on the outer shell. And the way that we got to 8 on the outer shell was that the hydrogen here was kind enough to share with. Okay, so there's our water molecule with the 10 electrons, which also means that there's 10 protons there, and everything was happy now, right? So this is really stable there. So if we put our little water molecule here in the middle, there's our H2O. Sometimes that water molecule undergoes changes. One of the changes it could undergo is if it deprotonates. And if it does so it loses a proton, then we would change it to a hydroxyl. So now we have an OH minus here. Right? Or rather than deprotonate, it could protonate, meaning it accepts another proton. And then we end up with hydronium, H3O. Right? So along this axis, you probably recognize it already. That's what pH describes, right? That's acidity, alkalinity, the potency of the proton, right? So along this axis here, we are going from an acid or acidic to alkaline And really what we have is that we have an abundance of protons here. So here's a high concentration, and here's a relative low concentration. Okay. And it's all described with this pH scale. Right? So we have pH, the potency of the proton, which was defined as the negative log of the concentration of our little friend, the proton. And what this axis basically describes is that, there is some kind of concentration average, right? So, and based on this definition, you already know what this is. So the pH is 7, so a log of concentration of this being such that we have a stable minute or stable concentration here. And then if we go into situations where we have a relative lack of protons, we have a strong tendency to accept protons because they're relative lack. Versus on this end, we have a relative abundance of protons. So we have a strong tendency to donate protons. So if I were to bring another substance in contact with either one of those conditions, we could predict which way protons would be moving. So that's what I'm trying to sell to you here. So let me write all this down. So on this end, we have a strong tendency to donate protons. And on this end, we have a strong tendency to accept them. Okay. So that's all fine and good. But things don't just move in this plane, they also move in another one. So now let's go to purple and say, aha. So our little water molecule up here, 10 electrons, 10 protons. What happens if rather than looking at the loss of protons, we look at the change in electrons? So what if we lose an electron? An electron loss, or we look at an electron gain. So if we are losing an electron, we call this oxidation. Okay? So an oxidation is a loss of an electron. Okay, so way back when I showed you the way that I remember this, oxidation is loss or oil. And the opposite of that was rig, which stood for a reduction is gain. Okay. So I don't know why chemists do it this way. A reduction is a gain and an oxidation is a loss. Okay? So there you have a way of remembering this. So the important thing though that comes out of it is that, well, the electrons in the sort of biochemical system, they're kind of a currency, right? The more you have of it, the more energy you have, the less of it you have, the less energy you have. So with our electron loss, we're also going to a low energy state versus we gain a bunch of electrons and we go to a high energy state. Okay. Now, when we looked at the pH scale, we said, strong tendency to accept protons, strong tendency to donate protons. You can already see where this is going on this axis, right? If we have a lot of electrons gained, we have a strong tendency to donate them. We have a strong tendency to accept them if we are on the low side. So, and again, the same thing. So now if we bring substances together that have a difference in this energy state, there's going to be an exchange in electrons. And that exchange in electrons frees up energy for the process. So a living thing, for example, might gain its energy from having access to this and having something available which is capable of accepting those electrons. So in this axis, we've described this all with pH. In the vertical axis, there's a very similar thing, and that's called the pE. Okay, so you could describe this all with pE, the potency of the electron, which is similarly defined, the minus log. Now it's the concentration of electrons. And just like it is with the pH scale, the center or the neutrality is defined based on a standard. Okay, so neutral means that we have conditions where pE equals 5.89 rather than 7. So that's the definition for neutral conditions in terms of the potency of the electron. There's another way that you can address this, and you could also say, oh, well, if there's a difference in electrons, I should be able to measure this as a voltage difference. And you can. And when we do that, it's called EH. So, and that EH is normally measured in millivolts. And you can indeed do this. You can take a non-polarizable electrode, stick it into your soil. You take a little voltmeter, and you can measure a voltage difference, which would tell you something about the tendency of that particular environment to either be gaining electrons or losing electrons. And that would tell you something about what kind of reactions are going on in this kind of soil. Okay? So the standard for EH, so the neutral conditions, would be for an EH, or let's say at a pH of 7, so neutral pH, then the EH would be equal to 470 millivolts. So that's just the standard. You don't have to remember those numbers, but it's, you know, we're defining a state as neutral, and that is the neutral state if that reads 470 millivolts. Okay. So, all right. So with this complicated business, I'll let you sleep over that, and then we'll reconvene on Wednesday, and then I'll tell you how all this mess here matters when we look into soils and organisms, and then hopefully you'll appreciate the benefit of looking at it in this kind of diagram. But before you run off, let me point out one more thing, and that is in soil environments and environments in general, these two axes they're coupled with each other, right? I mean, we don't just have a pH change and a pE change, but they change simultaneously. And there's a bit of a pattern to it, where most of this change happens along this direction here. Sometimes it can be this way too, but most everything that is life-related changes like such. Okay. So you go to alkaline conditions, you're automatically going to reduced conditions. You go to more acidic conditions, you tend to go to more oxidized conditions. So just as a general trend there, a lot of things work that way. Let me point this out in here as well. So highlighter, most life operates somewhere along this axis. And with that, I'm really done. I'll see you again on Wednesday.